Okay, so unit 12.2.2, we'll talk about the ionization constant of water. So we've talked about ionization constants or equilibrium constants so far. We're going to apply this to water, and we're going to link this up with acids and bases as well. So we've talked about pH and pOH last year a little bit. So you're familiar with these equations, or you should be, and as well with this one, but we probably never explained to you where they came from. So that's what I'm going to do right now. So to determine the degree of acidity of a solution, we're going to measure normally the pH, which is really the measurement of not the H plus ions, but the H3O plus ions. So the hydronium ions, as we saw in the last lesson. Now, when we measure that concentration, very often we're going to get a format like this, which is, as it says here, cumbersome, because there's a lot of zeros, there's a lot of decimals. So we tend to express this in the scientific format, which looks like this. For those of you who don't remember, the capital M means mole per liter. So when this number is converted into scientific notation, the exponent here, the -6, basically gives me the pH, which is a pH of 6. Now, it's all nice when I have 1 times 10 to the something, but if I don't have this type of concentration, then I have to work with these equations in order to go back and forth between pH and pOH and so on and so forth. Now, considering that the pH is directly linked to the concentration of H plus or H3O plus ions, basically they're interchangeable. I know that when I have a neutral substance, I have a pH of 7. When I have a pH of 7, that means that my concentration is 1 times 10 to the -7, right? So this corresponds to a pH of 7. Now, we may have shown you last year that there is a pH scale. So 7 is the neutral point, pH scale. But there's also what we call, and what we rarely use actually, but it still exists, a pOH scale. And it's basically a reverse image, a mirror image, I should say, of the pH scale. So something that is very acidic would be over here on this scale. So it's very acidic, it has a very low pH. On the converse scale, the reverse scale, something that is very basic would have a very small number, small reading on the pOH scale. Now on this scale here, something that has a very high pH is very basic. On this scale, something that is very acidic will have a very high pOH. So for example, if I have a pH of 2, okay, so it's very acidic. So 2 is 5 points away from 7. If I look on the other scale, 7 plus 5 is 12, right? So the converse on this scale would be 12. So a substance that is pH 2 would have a pOH of 12. Now 12 plus 2 gives me 14. So every time I go back and forth between the two scales, the sum of the pH and the pOH, because these two are basically equivalent depending on which scale I use, but they are equivalent, the sum will always give me 14. So that's where this comes from. Okay, so what do we do with this? Why do we need this? Let's look at an actual application of at least calculation. We're going to use this down the road. You're going to see how. Just in a nutshell, it's basically that most of the time when we have a neutralization situation, we have to dilute the acid into water and the base into water. And when those two dissociate, it affects the H plus ion concentration in the water solution. And same thing for the OH minus, because it's not only the acid and the base that produce those ions, but the water also dissociates to some extent. And so the water itself produces some H plus ions and some OH minus ions. So these equations take all that into consideration. The amount of ions produced by the water and the amount of ions produced by the acid and or the base. So that's why it's important that we understand this concept, because it will be in relation with the acids and bases concepts, related concepts we're going to cover down the road. Okay, so example A. Express in the form of pH, the hydronium ion, H3O plus concentration of this concentration in an aqueous solution. Is this acidic, neutral, or basic? So they're giving you the concentration of H3O plus, which they recopied over here, and they're asking you what is the pH. So if I have the concentration of H3O plus or H plus, again, same thing or same difference, what is the pH? So how do I find the pH if I have the concentration? I'm going to do minus log of the concentration, and I'll get the pH, which is what they did over here. It gives you a pH of 10.33, which is higher than 7, making it a basic solution. Example B, express a pOH of 3.6 in the form of an OH minus concentration. So I have a pOH of 3.6, and I want to know what is the concentration of OH minus. So I'm going to have to use the reverse. I want to find the concentration of OH minus, and I have the pOH. So I'm going to use this equation over here. So 10 to the negative pOH, or 10 to the negative 3.6 in this case, will give me the concentration of OH minus, which is 2.5 times 10 to the negative 4 mole per liter. Now, I was telling you before that water actually dissociates to form H plus and OH minus, or H3O plus and OH minus. How does this work? Well, I have two molecules of water that collide together, and one of them will lose an H plus, which will go and attach itself to this molecule, forming the H3O plus ion, and what am I left with? An OH minus ion. So that's as simple as that. Now I'm going to introduce a new constant. So that constant, it's a constant of equilibrium. So it's the constant for water. Now, if I may refresh your memory, a constant is products, concentration of the products over concentration of the reactants, right? But if you also remember, we do not use solids, we do not use liquids, because these are expressed as concentrations. So we only work with gases or with aqueous solutions. So if I write my equation, my products are H3O plus, OH minus, one times the other over the reactants. The reactant is H2O. Well, H2O is a pure liquid in this case, so I do not include it. That's why I crossed it out. So my Kw ends up being concentration of H3O plus times concentration of OH minus. Now we know that water alone is neutral. So water, 1 times 10 to the negative 7 would be the concentration here. 1 times 10 to the negative 7 would be the concentration here, because it's a neutral substance. A pH of 7 translates into this concentration of H plus or H3O plus. And again, something that's neutral, such as pure water, will give me a pOH of 7, which translates into this concentration of OH minus. 1 times the other gives me 1 times 10 to the negative 14. So that's where that number comes from. So here you have it. So now you have different tools to work around different situations. You have basically 6 equations to solve different types of problems. So that's it for now. I'll see you for 12.2.3. Ciao!